You can never directly observe anything crossing into a black hole. Imagine placing your adversary inside a rocket ship and launching it toward one. As the rocket approaches the black hole, gravity intensifies, and one might expect the rocket to accelerate. However, from your perspective, the opposite occurs. The rocket appears to slow down. Even the motion of your adversary, say, shaking their fist, seems to decelerate. This apparent slowdown is due to gravitational time dilation. As the rocket nears the event horizon, the boundary beyond which nothing, not even light, can escape, time appears to slow dramatically relative to an outside observer. At the precise moment the rocket would cross this boundary, it does not seem to vanish. Instead, it appears frozen in time. Meanwhile, the light emitted from the rocket becomes increasingly redshifted, growing dimmer and redder until it eventually fades from visibility altogether. In principle, light continues to be emitted from the point near the event horizon, meaning that one could theoretically observe all objects that have ever fallen toward the black hole, appearing frozen at its edge. However, in practice, light is emitted in discrete packets, photons, so there is always a final photon that escapes before crossing the horizon. As a result, these images gradually fade rather than persist indefinitely. This phenomenon is one of many unusual predictions arising from the general theory of relativity, our most accurate current description of gravity. Einstein's equations not only predict black holes but also suggest the existence of their theoretical counterparts, white holes. Furthermore, these equations imply the possibility of parallel universes and even hypothetical connections between them, known as wormholes. The development of general relativity was motivated in part by a limitation in Newtonian gravity. In the 17th century, Isaac Newton proposed that all objects with mass attract one another through a force acting at a distance. However, Newton himself found this idea troubling, questioning how such forces could act across empty space without any intermediary. Over 2 centuries later, Albert Einstein resolved this issue by proposing that gravity is not a force acting at a distance. Instead, mass and energy curve the fabric of spacetime itself. Objects like planets follow paths determined by this curvature. For example, Earth orbits the Sun not because it is pulled by a force, but because it moves along the curved spacetime created by the Sun's mass. This framework eliminates the need for instantaneous action at a distance. Mathematically, this relationship is described by Einstein's field equations. These equations relate the distribution of matter and energy to the curvature of spacetime. Although often written compactly as a single expression, they actually represent a complex system of coupled differential equations, making them extremely challenging to solve. To better understand solutions to these equations, physicists use spacetime diagrams. Imagine a flash of light expanding outward in all directions. This expanding sphere defines the boundary of all possible future events you can influence, your future light cone. Conversely, incoming light defines your past light cone, encompassing all events that could have influenced you. In flat spacetime, the geometry is simple, and the separation between events is described by a straightforward formula known as the spacetime interval. However, near massive objects, spacetime becomes curved, and this formula must be modified accordingly. Solutions to Einstein's equations provide these modified geometries. In 1915, shortly after Einstein published his theory, Karl Schwarzschild found the first exact solution. He considered a simplified case, a static, spherically symmetric mass with no charge or rotation. His solution, now known as the Schwarzschild metric, describes how spacetime behaves around such an object. Far from the mass, spacetime is nearly flat, but as one approaches it, curvature increases and time slows. However, this solution revealed 2 problematic points. One at the center, a true physical singularity where density becomes infinite, and another at a specific radius, now called the Schwarzschild radius. Initially, both were thought to be singularities, but later work showed that the latter is merely a coordinate artifact. It corresponds to the event horizon, the boundary of a black hole. Early scientists doubted the physical reality of black holes, as their formation required extreme conditions. Studies of stellar evolution suggested that collapsing stars would be supported by quantum mechanical pressures, such as electron degeneracy pressure, leading to white dwarfs. Later, neutron degeneracy pressure was found to support neutron stars. However, these mechanisms also have limits. Beyond a certain mass, no known force can prevent gravitational collapse. Research by Oppenheimer and others demonstrated that sufficiently massive stars must collapse indefinitely, leading to the formation of black holes. A key insight resolved the apparent paradox. While an external observer never sees an object cross the event horizon, an observer falling into the black hole experiences nothing unusual at that boundary and passes through it in finite time. This difference arises from the nature of spacetime itself. Modern spacetime diagrams, such as Kruskal-Szekeres and Penrose diagrams, reveal that the singularity inside a black hole is not a location in space but a moment in time, the inevitable future for anything that crosses the horizon.